Let us discuss chapter 5. Chapter 5 is on chemical reactions. We have already learned how to draw structures. We know about the valence electrons. We know about the charges. We know about polyatomic ions, monatomic ions. We know about metals, non-metals, ionic bonds, covalent bonds. Now it's time to do the actual reactions. Here are the learning objectives. We need to write and balance chemical equations. We need to classify chemical reactions as combination, decomposition, single displacement, double replacement. You can call it single displacement or replacement, double replacement or displacement. We also need to define oxidation and reduction reactions and recognize the species and the components in the redox reactions, those that are oxidized, those that are reduced. We need to identify those. Later on, we'll define what a mole is, the unifying factor in calculations and of quantities in chemical reactions, and use Avogadro's number in calculations. The same Avogadro's number will help us to define what a mole is. Then we will calculate the formula weight and molar masses of compounds and relate the mass of a substance to the number of moles and Avogadro's number. We'll carry out mole mass calculations in chemical reactions based on reacting ratios, and then we'll determine percent yield at the end and determine limiting reactants and also theoretical yields. Okay, so we have a lot to do. Let's introduce the chapter Introduction to Chemical Reactions. Now, to remind you, a physical change only changes the physical state of a substance, but it does not change its composition. An example here is given, that of water. The formula of H2O is just this, you know, the Lewis structure of water. And if this is in solid state, what people call ice, the formula is the same. If you melt the ice from solid state to liquid state, you get liquid water. Guess what? The formula stays the same. Okay? The composition is the same, but this time is going to be liquid, in liquid state. So that's how you know that the process has undergone a physical or a chemical change. In here, you're looking at an ice. I don't know if that's an iceberg in the ocean, but here you're looking at water. Around here, you're looking at the water in liquid state. So still, this is water in solid state, but this is water in liquid state. The iceberg is melting down to give you the liquid state. It's the same H2O. So that's a physical process. In this chapter, we are talking chemical reactions. So we will transform the reactants to products which are different in chemical composition. That said, a chemical change is a chemical reaction that converts one substance to another. It's very easy to tell. Like if you have chlorine gas reacting with hydrogen gas to give us HCl, that is something completely different than what we started with. That is a chemical reaction. In this case, you have a Cl and a Cl, a hydrogen and a hydrogen, and in this case, there is breaking of bonds, right? This breaking of bonds. Imagine this hydrogen and this chlorine combining to give you HCl, and then the other one, this chlorine and this hydrogen combining to give you HCl, and that gives us the two molecules of HCl. So you are breaking bonds and you are forming bonds. So in chemical reaction, there is breaking of bonds, which requires energy. We say it's endothermic, and usually the bonds you're breaking are on the left side of the reaction. We call them reactants. These are the reactants, and on the right side, those are the products, and this arrow just says to yield or to give. So the left side is reacting to give or to yield the right side. There is formation of new bonds on the right side, what we call products. Another example is shown down here of a chemical reaction. Imagine CH4 methane reacting with oxygen gas. This is an oxidation reaction because you are adding oxygen to the carbon. Now, if these two are reacting, a chemical reaction happening to give us CO2 and water, you can tell that we ended up with completely different substances. In this case, you have CO2 and you have water. So bonds are formed on the right side, but on this other side, the CH bonds are broken. The CH bonds are broken, including the OO, oxygen double bond. Okay, so on the reactant sides, there is bond breaking. On the product side, bonds formed. As the bonds are formed, you make new substances. We are going now to learn how to write chemical equations. A chemical equation is one that uses chemical formula and other simple symbols to show what reactants are starting materials in a reaction and what products are formed. So characteristic of a chemical equation, you have to have chemical symbols on the left side of it. Those will be reactants reacting to give you products written as chemical symbols, and it's still gonna be balanced. So on the left side is gonna be the reactants, on the right side will be the products, and the numbers before the symbols of the chemicals reacting or formed will be the numbers that are counting the number of molecules of a given element or compound that react or is formed. Let's look at an example. Usually the chemical equation starts or it's derived from a word equation. So for example, suppose methane reacts with, that's what the plus means, reacts with oxygen gas. So methane is a gas, reacts with oxygen gas to give, that's what that arrow means, to this arrow right here means to yield or to give or to produce or to form, whichever synonym. Methane gas and oxygen react to give, to form, to produce, to yield carbon dioxide gas and water. That is the word equation. This is the word equation of reaction. If we want to generate the chemical equation of reaction from this, we would then use chemical symbols. So it will be the formula of methane is that, the formula of oxygen is that, formula of carbon dioxide is CO2, formula of water is CH2O. Now this equation is not balanced. Usually there's a law of conservation of mass. You cannot just lose mass, you cannot just lose matter, it must be converted to something else. Okay, so to balance this out, we usually put a 2 here, and we'll talk about balancing chemical equations in this chapter. And we'll also put a 2 there. Why so? I want to make sure I have 4 oxygens here, and I also have, if I add on this side, I also have 4 oxygens on the left side. I also want to make sure I have 4 hydrogens and 4 hydrogens. The subscript in the formula must never be changed. I also want to make sure on the left I have 1 carbon, on the right I have 1 carbon. You balance by inspection. So these numbers that are helping us to balance the elements on product and reactant side are what we call coefficients. Okay, they show the number of molecules of a given element or a compound that react or is formed. Okay, so remember again, on the left side it's always the reactants. They react to give, to yield products on the right side. Like I mentioned, there's a law of conservation of mass that states that atoms cannot be created or destroyed in a chemical reactions. They are just transformed to other molecules or combined in a different way to give you something different, a different molecule. Coefficients are used to balance the chemical equation like I showed before. A balanced chemical equation has the same number of atoms of each element on both sides of the equation. Let's do some atom economy. That's what we call it. Economy and accounting. So let's account for some atoms. This, remember, is the reaction arrow. That means to give or to yield or to form. So our atoms in the reactant side right now, as it's balanced already, I showed you how to balance this, but we'll talk about it in details. On the reactant side, we have one carbon. There he is. We have 4 hydrogens. Let me use color codes. We have 4 hydrogens. There he is. Let me go to the right. How many hydrogens do we have? 1, 2, 3, 4. 2 times 2. We also have 4 hydrogens, and I can tell that I still have 1 carbon. So those two are balancing so far, just to check if our equation is balanced right now. And then I see that I have 2 times 2 oxygens. I have 4 oxygen atoms, the red ones. And then I have 2 oxygens here. And then 2 times 1 is 2. I also have 2 oxygens there. If you add them together, they give us 4 oxygens, which is what we have down here. That equation is balanced. Again, these numbers before the molecules are what we call the leading coefficients. They help us to balance it. Okay. Color code is used so you can tell. If you're looking at the black ball, that's a carbon. These white ones are hydrogens. And then the red ones are oxygens. Let us consider this general reaction. Sodium hydrogen carbonate plus HCl to give us CO2 plus water plus NaCl. This arrow right there, which is this, means the reaction arrow, or to give, yield, or produce, or even form. Whenever you have a triangle in the reaction, that's just the symbol of heat. Now suppose that I have sodium bicarbonate in solid state. I put it as a subscript, so that's what S means. Suppose this is HCl in water, so it's gonna be aqueous solution. Aqueous just means the chemical is in water, like aqua. And then CO2 is bubbles produced during this reaction, so we put G to say we have a gas formed. Let's say this is L. That would be liquid. Some liquid water is formed. And then NaCl, will put it as AQ because it's gonna be dissolved in the water. So this is the kind of symbols that we use in chemical reactions. Using these chemical reaction as an example, did I balance it? Let me see. I think it is balanced as is. Let us do some more examples on balancing chemical equations. We're still learning on how to balance a chemical equation in this section 5.2. Example: write a balanced chemical equation for the reaction of propane with oxygen to form carbon dioxide and water. So step number 1 that I'll follow will be to write the equation with the correct formula. That should be my step number 1. I have to write the equation with the correct formula. The word chemical reaction will be, we are given propane is reacting with or in oxygen to give carbon dioxide and water as a product. So we want to write the word equation to our chemical equation of reaction, and that will involve writing our propane with the chemical formula of propane. Oxygen formula is like that. Carbon dioxide is written as CO2. Water is H2O. Now the subscripts in the formula can never and should never and must never be changed to balance an equation. You keep those subscripts that came with the formula of the substance as they are. You keep them intact, because if you change any of those subscripts, the identity of the compound is going to change. So once you confirm that those are correct, the next thing you want now to do is to include the leading coefficients. Coefficients are just numbers that helps us to balance the chemical reaction, where the number of elements on the left side should be equal to the number on the right side, following the law of conservation of mass. The law of conservation of mass that states that atoms cannot be created or destroyed in a chemical reaction. We do know that they are conserved. You're just converting them from one substance formula to another. So let's start by balancing what we are given. We know that the chemical reaction is this. If you look closely, the elements are not balancing left and right in terms of number or in terms of count. One of those is carbon. I have 3 carbons here. This is like, if you write CO2, is like saying C1O2. The 1 is implied. You have 1 carbon here, you have 3 carbons here. That's not balanced. So let's balance the carbons first. And usually if there's a metal, we balance the metal before the non-metal. So I see I have 3 here, C3. So to balance my CO2, I will not put the 3 down here there. No, that one will change the CO2 entirely, and there's nothing like that that exists. There's nothing like that that exists. So you don't want to change the subscript. Instead, we put a 3 before the CO2. Okay, and now that 3 is multiplying both the carbon and the number of oxygens, so you have to keep in mind. So now we've balanced our carbon, okay, but the problem is the oxygen is affected. Let's now look at the hydrogens. The hydrogen balance, no, we have 8 hydrogens here, yet we have 2 hydrogens there. What do I do to make these hydrogens 8? I would put 4 there, yes, right? Don't change the 2 and put 8 there. No, put the 4 as a coefficient. Now I see I have 8 hydrogens, but again the number of oxygens are multiplied to 4. So now if you are to count the number of oxygens here, 3 times 2, I have 6 oxygens on the right side, and 4 times 1, I have 4 oxygens from the 4 waters. This tells me that on the right side I have 10 oxygens, which came after I tried to balance the carbon and the hydrogen. Alright, so from this point we know our hydrogens are balanced by putting the 4 here, and of course our carbon is balanced by putting the 3 there. And now I've shown you that we need to have 10, we now have 10 oxygens on the right side. So we have to take care of that. I've shown you how we get 10 oxygens on the right side. In CO2 is 3 times 2, which gives us 6 oxygens. In water is 4 times 1, which gives us 4 oxygens. You add these up, you're going to get 10 oxygens, which is what this is showing. On the left side, originally, we just had O2. To make the left side have 10 oxygens, we'll put or introduce a 5. We'll introduce a 5. So now 5 times the 2 gives us 10 oxygens. In this case, everything is now balanced. And so our balanced formula will be like this. and it shows that everything is balanced. And if you can try to check, you can check the atoms. On the left side you have 3 carbons, 8 hydrogens, 10 oxygens. On the right we have 3 carbons still, 6 oxygens plus 4 oxygens gives you 10 oxygens, and 4 times 2 hydrogens gives you 8 hydrogens. So everyone is balanced, big, happy smile. Okay, so that is how you balance chemical reactions, and we're going to do more practice. Maybe I'll show you 3 examples. Okay, let us do examples of balancing chemical equations. Let's balance this first one. Let us balance this first equation. So by inspection, which is what we are doing, we're balancing by inspection, I would start with the nitrogen. I see I have 2 nitrogens here, I have 2 nitrogens here. So looks like that is fine. And then I look at the oxygens. I have 5 oxygens here, I have 2 oxygens here. They are not balancing on the left and right. So what would I do to make sure that the left side is equal to the right side? What should I do? The best way to do this is to even them out. I would use 5 because that is the closest number that can be divided by 5 and 2 before the oxygen. And then I would use 2 here. So that will help me to get 5 times 2, that will be 10 oxygens. And then this side for the oxygen will be 2 times 5, gives me 10 oxygens. Okay, now by doing so, there's a problem I've created. The nitrogens are no longer happy. This time that makes this nitrogen 2 times 2, because that 2 is the coefficient. It multiplies everything in the formula. It gives me 4 nitrogen. Here I see I only have 2 nitrogens, so to make this 2 4, I'll put 2 there. And that would be 2 times 2 to give me 4 nitrogens. Now I come back and inspect on the left side. How many nitrogens? 4. How many oxygens? 2 times 5. 2 times 5, 10. Okay, come here. How many nitrogens? 2 times 2, 4. How many oxygens? Oxygens will be 5 times 2, 10. Everything happy. So the balanced equation is 2-dinitrogen pentoxide. That's a covalent molecule. That will be the name. Decomposes. This one decomposes to give me 2 molecules of nitrogen gas and 5 molecules of oxygen gas, balanced. Let's do the second one. In this case, I'll still start balancing the first element, the metal. I see I have 1, this is Fe1. I have 1 ion, but I have 2 of them here. There's 1 here implied. 1 times 2 is 2. So I have 2 Fe, and I have 1 Fe. 1 times 1. There's a 1 here, there's a 1 as a subscript. 1 times 1 is 1. So there's a problem. How do I balance the Fe? I do so by putting 2. Now it's going to be 2 times 1. So for the ion, I have 2 times 1. Now it's 2 Fe. On the reactant side, on the product side, the ion is 1 times 2. That means I have 2 Fe. Happy. The next thing I'll want to balance is going to be my nitrate. This one is polyatomic, so I can balance it. I can balance it easily, knowing that I have a polyatomic ion here. How many nitrates do I have? I'm going to balance it as a group to make it easy because it's polyatomic. Those elements move as a group. So for the nitrate, I see that I have how many? 2 times 3. So 2 times 3 nitrates, that gives me 6 nitrates. Okay, now here there's 1. If I multiply that by the 2, currently I have 2 nitrates. How do I make the 2 nitrates to be 6? To do so, I'm going to put a 3 here, so that now I have 3 here times 2. Okay, so I had 2 nitrates on the right side. Here I have 6. I'm looking at the group NO3, balancing nitrogen and oxygen all together. The placement of the leading coefficient number 3 here will make my nitrate to be 6, because now I'm going to say it's 3 times subscript 2. That gives me 6 nitrates. Now, doing so, the magnesium here is affected. This is currently telling me that my magnesium here, I have 3 magnesiums, right? 3 times 1 is 3. On the left side, how many magnesium do I have? Only 1. So to balance it, I will introduce a 3. So that will give me, for the magnesium here, it will be 3 magnesium. Now, let's look at this oxygen. There are 3 oxygens there that came with it. So the extra, let me just call them extra oxygens. They have to be balanced. On this right side, it's 3 of them. 3 times 1, subscript 1 on oxygen. So 3 oxygens on this side. On this side, how many extra oxygens I have? I have 3 times 1. I'm just going to call them extra oxygens. Will be 3 times 1, so it's 3 oxygens. Okay, so now that one will help me to balance everything together. Now, if you want to put everything together and try to see if you have balanced it, to confirm it, because I know I balanced the nitrate as a group. Let's start with Fe. On the left side, Fe, there are 2 Fe. Okay, on the right side, subscript Fe, 2 Fe. Okay, now we go to the nitrogen. Just focus on the nitrogen by itself, just the nitrogen. 3 times 1 of the nitrogen times 2, that's going to give you, so nitrogen on the left side, it's 2 times the 1, the subscript on the nitrogen, times the 3, the subscript of the polyatomic ion, is going to give me 6 nitrogens. It's going to give me 6 nitrogens. Okay, focus on the oxygen. The oxygens here is 3 times 3 times 2. So oxygen will be 3 times 3 times 2. But we do have other oxygens here, 3 times 1. If you add all these together, this is going to be on the left. Here it's going to be 18 plus 3 is giving me 21. So we have 21 oxygens. Let's go to the right side. How many oxygens? Oxygens on the right side, those are oxygens we are talking about. We have 3 times 1, or 1 times 3 plus, and then down here we have 2 times 3 times the red 3. So you have 3 times 3 times 2. This 3 multiplies the 3 inside the parentheses and is multiplied by the 2 under the polyatomic ion. If I add all this together to be 3 plus 18 again, that's 21. That's 21 oxygens. So I'm counting for you atom by atom. Okay, so how about the nitrogen on the right side? Is 3, the red 3 times the 1 subscript on the nitrogen times 2. So I'll go 3 times 1 times 2, and that's gonna be 6 nitrogens. So everything is balanced. So the balanced equation will have 2, 3, 1, 3. That will be the balanced equation. Now let's look at the following example, which is example number 3. We need to balance the combustion of octane. which is found in gasoline in gas for your vehicles. Combustion of octane in oxygen to give us carbon dioxide and water. So again, we start off by trying to balance the carbon. I see there are 8 on the left. On the right side, there's only 1 carbon, so I will not put 8 down here to balance it. That's a felony in chemistry. We'll want to put it there as a leading coefficient. So keep this one having a 1. Okay, and then let's go to the hydrogens. I have 18 hydrogens, but here I see that I only have 2 hydrogens. How do I make them 18? I probably put a 9 there. Okay, because if I put a 9 there, then it would be 9 times 2 equals to 18 hydrogens. Okay, 9 times the 2 subscript is 18. Now we come to the oxygens. Here I see I have 2 oxygens, but then on the right side, looking at the oxygens, I have 16 oxygens here, 8 times 2. And here I have 9 oxygen, 9 times 1. Okay, so if I take 16 plus 9, that will give me 25. That gives me 25 oxygens. Now, is that going to help me? Let's see what we'll do. So I have 16, I have 9. Okay, so now to balance this off, then I'll have to put here, I need 25 oxygens on the left, so this one will have to be 25 over 2, because if I do 25 over 2 times the subscript, it's gonna give me 25 oxygens. There's a rule that elements usually combine in whole number ratios, so we don't want to have this fraction here. So we're going to multiply everything by 2. We're going to multiply this by 2. We'll multiply that by 2. Why? Because we want to get rid of the 2 denominator. And then we multiply this by 2 and multiply that by 2. I'm multiplying everything by 2 to get rid of this denominator. What you do to one, you do to all. So the new balanced equation will be 2, 25, 16, 2 times 8 is 16, 2 times 9 is 18. Those are the leading coefficients, and now I can bring in my molecules. 25 oxygens will give me 16 CO2s and 18 H2Os. That's supposed to be the balanced equation. Now if you check all elements, you'll find that they all balance out. That's how to do it.